NASA's Earth Science Division missions help us to understand our planet's interconnected systems from the global scale down to the minute processes. NASA Earth Science delivers the technology, expertise, and global observations that help us to map the myriad connections between our planet's vital processes and the effects of ongoing natural and human-caused changes. Using observations from satellites, instruments on the International Space Station, airplanes, balloons, ships, and even on the land, our researchers collect data about the science of our planet's atmospheric motion and composition, land cover, land use and vegetation, ocean currents, temperatures and upper ocean life, and ice on land and in the sea. These data sets, which cover even the most remote areas of Earth, are freely and openly available to anyone. So today I'd like to just take a moment and introduce all of us as speakers. My name is Cynthia Hall, and I am with the NASA's Earth Science Data Systems Program. We'll also hear from Heidi Christensen from NASA's Alaska Satellite Facility Distributed Active Archive Center, or ASF DAC. Helen Baldwin from NASA Surveyor, although she is unable to make it today. She's from Surveyor Amazonia. And Africa Flores, also from NASA Surveyor Land Cover and Ecosystem. And just to give you a little bit of background, ASF DAC is the DAC that archives and distributes NASA and partnering agencies' SAR data. And Surveyor works with developing countries to use satellite data to address critical challenges in food security, water, land use, disasters, and even water quality. Here is our agenda for the day, and please note that all times are in Eastern Standard Time. After I give a brief introduction of NASA Earth Science Data and the Earth Data website and resources for finding and getting started with SAR data sets, Heidi is going to talk about what SAR actually is and introduce the SAR data sets that are available at the DAC. Then we'll take a short break at 2:10 just to allow you to get some water, coffee, or walk around for a minute, what have you. And then after the break, we're going to work through some use cases. Heidi will take us through an interferometric SAR workflow, and then we'll take another break at 3:30, and then Africa will take us through a land cover change use case and a forest stand height use case. And then we'll finish up with questions. We are developing a web page on Earth data for this course. I'll put the link in the chat shortly, but we will keep the web page on Earth data, so you'll still be able to access the materials after the course. It includes all the materials from our workshop last year as well, and it is different from this year, and we'll just continue adding to it as time goes on. So hopefully it'll be a great resource for you. So when most people hear NASA, they think of space, not Earth. But NASA does have a strong Earth Science division, and the division uses the vantage of space to study the Earth processes that power climate, weather, and natural hazards, and the impact of those processes on life on Earth. And NASA gathers information about the Earth from a fleet of Earth observing satellites, as you can see here. This slide are many of those operational satellites. The operational ones are in blue and green, and we are currently collecting measurements from those. Those that are in development are in orange, and those in the planning stages are in yellow. One of our upcoming missions that we're really excited about is called NISAR. It's the NASA Indian Space Research Organization SAR mission, and it's a mission that's planned to launch next year in 2022, and it's going to provide global SAR coverage. It's also increasing our data archives tremendously, and so we're moving into the cloud more and that kind of thing. But it's really an exciting upcoming mission for us, and one that'll, I think, be exciting for all of you. The fleet of satellites that you just saw allow NASA to gather information about the entire Earth system. And on the left side of the slide, there's a partial list of some of these observations and measurements that NASA collects through its orbital, airborne, and field programs. So within the disciplines of atmosphere, ocean, cryosphere, land, and even human dimensions. Specifically, the Earth Science Data Systems Program actively manages NASA's Earth Science data as a national asset, whether it comes from the satellites, the airborne, or the field data. We believe the data are valuable, not just while the mission operates, but well into the future. And so our job is to develop data system capabilities that support rigorous science, as well as interdisciplinary research, applications use, and even commercial use. And we make sure that the data are quality controlled, have the necessary metadata, and work well with other data, so it can be used by anyone who needs it. And of course, as I mentioned before, NASA data is free and open. And this philosophy includes tools and services on our Earth Data website and at all of the DACs. And finally, we do work to engage the earth science community in our efforts so that we can understand user needs when developing our data systems. And this is just a cool example of NASA earth science data being used for geology. These are raised beaches around the Hudson Bay in Canada's Ontario province, and it shows how the landscape rebounded after the last ice age. So as I mentioned, one of our core philosophies is making sure the data are discoverable and usable to the broader community. Within NASA's data systems, open source science serves as the foundation of the program. And what that means is the open sharing of data, information, and knowledge within the scientific and application communities and the wider public so that we can accelerate scientific research and understanding around the world. NASA open data policies are helping break down barriers to using NASA Earth science data and foster a more collaborative, inclusive scientific process, open to anyone, regardless of background, ethnicity, gender, or geographic location. Our activities support the open source science ecosystem and its core principles, and that is to shorten the time it takes for a new user to find and learn how to use the data, increase the community contributions by allowing for integration of data, explore and exploit data in new ways, such as geospatial web services, interactive web maps, and different applications, incentivize and energize innovation, and then complement efforts and enhance integration with Earth-focused missions. Just to give you some background about the collection, the Earth Observing System Data and Information System, or EOSDIS, is a key core capability in our program. And I'll go ahead and apologize in advance for all the acronyms we here at NASA, just believe in those. It's the largest repository of earth science data in the world. We currently archive more than 40 petabytes of earth science data. This is twice the volume of information as the entire collection of the Library of Congress. And specifically with some upcoming missions, including NISAR, that number is going to skyrocket. EOSDIS archives include over 34,000 and growing data collections that have been used by more than 570,000 unique users. And this data also includes some near real-time data that is made available to the public within 3 hours of observation. And all of this data can be accessed through the Earth Data website and through the DACs. So speaking of DACs, those are distributed active archive centers, and that's where the data are processed, archived, documented, and distributed. The DACs also assist users in selecting and obtaining the data, provide access to data handling and visualization tools, notify users of data-related news, provide technical support, and they're always happy to answer questions. And they are organized by scientific discipline. We have an Earth Data Forum, which is a location where you can ask a question and then a subject matter expert from one of the DACs will answer your question. And if the DACs are not part of the larger forum, they usually have their own frequently asked questions. So DACs that are specific to geological data, the Crustal Dynamics Data Information System supports space geodesy and geodynamics. And the CDIS archives and distributes mainly global navigation satellite systems, or GNSS, data, which include GPS. And these are primarily used by the geophysics community. The Alaska Satellite Facility, or ASF DAC, operates the NASA archive of synthetic aperture radar data from a variety of satellites and aircraft, and provides these data and associated support services to Earth scientists. In fact, this map was made with Sentinel-1 data archived at ASF and shows the total subsidence in part of the San Joaquin Valley in California between May 2015 and September 2015, The areas of most extensive subsidence appear in shades of yellow and bright green. The Land Processes, or LPDAC, is a partnership between USGS and NASA, and that DAC supports land data, remote sensing data collected by sensors. And these are mainly used by researchers studying land dynamics and environmental systems. And then finally, we have the Physical Oceanography, or PODAC, which hosts all of our ocean data. Earth Data is our centralized website that allows access to data at any of the DACs. Earth Data has two important resources to help you find data. On the left, Earth Data Search is a more data-centric option. Users can search for data across all of the DACs by choosing what they want to measure or what instrument they are interested in. So you really can use a search term to find the data that you need. Worldview on the right here is a more visual search, imagery-based. It allows the user to zoom in on an area, preview the data sets that are available for that region, or overlapping data sets to see how they might work together. You can also create animations like you see here. I'm going to talk about and show these resources later so that we can have an idea of what we're dealing with here. But even with these tools, this can still be confusing to a more novice user. So I'm also going to spend some time talking about several resources to help users get started.